Hi, now we are going to take a new chapter, work power energy, second part. Work, energy and power. First we will define what is called work done. When the force is applied to the body, that force makes the body to displace. That is, the body is displaced because of the applied force. Work is said to be done when the force is applied to a body to displace it. That is a simple concept. Definition wise, that is the thing. Formula says F dot dr. That is the scalar product of two vectors. W is equal to F dot dr. Scalar product of two vectors. That is F dr cos theta. Suppose if you take, this is the displacement direction and this is the force direction, making an angle theta. Then along the direction of displacement, the component of force, F cos theta, you can resolve the force into two components. If it is not acting exactly horizontal or exactly vertical, you can resolve it into two components. Vertical direction, horizontal direction. So this is theta means horizontal component is F cos theta, vertical component is F sin theta. So I can write along the direction of displacement F cos theta into dr, we call it as work done. Unit is joule. Work done can be zero. Work done is zero for three different cases. First case, when F is equal to 0, W is equal to 0. Sir, you said you have to apply a force to make the body displaced. Then if the force is not applied, the work done is 0. You are applying a force now, sir. You consider an example, the body moving in a frictionless surface, smooth polished surface. The body will continue to move without applying any force. Initial force is applied to displace. After that, it will continue to move because there is no frictional force. Body comes to rest only if there is a frictional force. If there is no frictional force, the body continues to move. So that is called F is equal to 0. Second case, when displacement dr is 0, W is equal to 0. Displacement dr 0 means suppose you are pushing a wall. You are applying a force. You are pushing a wall. Wall cannot move. The body is not displaced. By applying a force, the body should be displaced. That is the definition of work done. So here, the body is not displaced. So there is no question of work done here. Work done is 0. Third case, when F and dr are perpendicular to each other. Perpendicular means, suppose a person is carrying a box on his head or in the hand, he is moving. Moving in the forward direction means this is the displacement. Force and displacement. Force and displacement, theta is 90. W is equal to F dr cos theta. Here theta 90, cos 90 is 0. So I can say force is, that is work done is 0. Simple concept, man. 3 cases of work done 0. Force is 0 means work done 0. Displacement is 0 means work done is 0. And force and displacement are perpendicular means work done is 0. So these are the 3 cases. And next part is negative work done. Negative work done. Most of the example what we come across in our day-to-day life is theta is equal to 0. That means when you apply a force, in that direction only body is moving. Along the direction body is moving. So theta is equal to 0. W is equal to F dr. Cos 0 is 1. Okay. Negative work done. When theta is equal to 180, W is equal to minus F dr. Cos 180 is minus 1. If you apply a force, body should move in the opposite direction. Sir, how it is possible, sir? You are applying a force in this direction, how the body will move in the opposite direction? You can take a very simple example. Suppose a person is kicking a football. Goalkeeper stops it. That is theta is equal to 180. At the time of kicking, theta 0. But the moment the goalkeeper stops and the body returns, that itself is theta is equal to 180, negative work done in this case. Okay, simple. Next. Work done by constant force. What is the formula for work done here? W is equal to F vector dot dr vector. Suppose the work done is small work done dw. Then I can say integral dw is equal to integral f dr cos theta. What is called integration? Here, simple word I am telling you. Integration is nothing but a summation series. Small values, if you add the total value, we call it as integration. So integration is nothing but a summation series. Okay, so W is equal to R1 to R2, initial displacement, final displacement. So I can write F dr cos theta, F cos theta, constant force. So F cos theta, you take it outside, integral dr, R1 to R2. W is equal to F cos theta, integral dr is R. I can write limit R1 to R2. Integral dr is R1 to R2. So I can write W is equal to F cos theta into R2 minus R1, upper limit minus lower limit. This is work done by constant force. Graphically also I can explain. That is displacement R in x-axis, F cos theta in y-axis. Displacement is constant. F cos theta variable, constant force. Displacement is constant. Theta is varying. F is the product, F cos theta is constant. So this we call it as work done by constant. The area of the graph will give you the work done. R1, R2, initial work done. So W is equal to area ABC. Any graph you take, the area of the graph will be product of x-axis and y-axis. Product of x-axis and y-axis means f cos theta into r. So f cos theta r we call it as area of the graph. Area of the graph in this case is product of f cos theta and r is what? That is called work done. So both are same. F cos theta into dr value and area ABCD both will give you same answer. W is equal to f dr cos theta or W is equal to area of the graph ABC. Initial displacement, final displacement R1. Okay. Now work done by variable force. Work done by variable force. What we have seen is constant force. Variable force means same graph, displacement in x-axis, f cos theta in y-axis. Here f and theta are variables. It is not constant. So you will not get a straight line, but it is a variable. We don't know. You take some 10 values, plot it. All the 10 values, f and theta are variable. So calculate f cos theta, put it in y-axis, displacement in x-axis. Small portion. Every value you have taken small portion. Join all. Combine all the areas. This is work done by this area of the graph, ABCD. Is nothing but the work done by variable force. You calculate this strip area and then add everything, or you calculate the total area, f cos theta into r. Total area you calculate. Both will give you same answer. Work done by variable force. Correct, Amma? Simple. Next, energy. Capacity of doing work, we call it as energy. That is the definition of energy. Capacity to do the work. It is a manifestation of work. That's all. Simple. Unit of energy and unit of work done, both are same, joules. Dimensional formula falls into displacement. So energy is equal to work done. That is Fs or Fr or Ft or anything you can take. Unit wise Newton meter or joules. Dimensional formula force, you know, ml t power minus 2 into displacement L. So you will get ml square t power minus 2. Dimensional formula of energy. Energy we have many types. Here we are going to focus only on mechanical energy. Heat energy, light energy, nuclear energy, chemical energy. You have got various forms of energy. Here we are going to focus only mechanical energy. Mechanical energy, two types. kinetic energy, potential energy. Kinetic energy, potential energy are the two types of energy here. What is called kinetic energy, sir? Energy possessed by the body by virtue of its motion. Kinetic energy. Energy possessed by the body by virtue of its motion, we call it as kinetic energy. Expression wise, kinetic energy is half mv square. It is also work done, force into displacement. Work energy theorem, that's what it says. You can prove kinetic energy of mv square. Work energy theorem is nothing but change in kinetic energy, is nothing but work done. That is called work energy theorem. Change in energy, kinetic energy is equal to work done. How can you say this is work done, sir? We will explain. Work done formula is force into displacement. Assume the body is moving along the direction of force. So theta is equal to 0 here. So cos 0 is 1. Fr or Fdr or Fs, everything work done. By Newton's second law, we know F is equal to ma. From equation of motion, we know V square is equal to U square plus 2as. One equation we have. V is the final velocity of the body. U is the initial velocity of the body. A is the acceleration. S is the displacement. If initial velocity is 0, then we can write V square is equal to 2as. If U is equal to 0, 2as is equal to V square. A is equal to V square by 2s. Then I can write F is equal to mass into, instead of A, I can write V square by 2s. Therefore, work done is nothing but energy possessed by the body by virtue of its motion. So that is kinetic energy. Formula F into S. What is F now? mv square by 2s into displacement is S. Cancel. Half mv square. No, sir. Initial velocity is not 0. You are calculating when the body is moving from point A to the point B. Already the body is in motion. Between 2 points, you want to calculate kinetic energy. Then initial velocity is U, final velocity is V. Velocity is not constant, changing. In that case, you can write what? If U not equal to 0, then 2as is equal to B square minus U square. A is equal to B square minus U square by 2s. Therefore, F is equal to M into V square minus U square by 2s. Then you can write work done is F into S. What is F? M into V square minus U square by 2S into S. Cancel half M V square minus half M U square. V is the final velocity and U is the initial velocity. So I can write final kinetic energy minus initial kinetic energy. That is W. So this is nothing but change in kinetic energy. This is the famous work energy theorem. So same definition. Kinetic energy half mv square. You can write here itself. Kinetic energy. Initially, velocity is 0 means you can take this part is 0 and this one you can write. So this is about kinetic energy and work energy. Okay. Next. Relation between momentum and energy. Relation between momentum P and energy. Okay, what is the formula for kinetic energy here? Kinetic energy is half mv square. Multiply and divide by m into v square. Take this m here, 1 by 2m. I am having m square v square. M square I am writing it as m. V square I am taking it as v into another mv. So m square v square I am writing as mv into mv. You know very well mv is nothing but momentum. So I can write kinetic energy is equal to 1 by 2m into p, where p is called mass into velocity called momentum. So kinetic energy is mv is momentum, here mv, so it will become p square. So p square by 2m is kinetic energy. Now that I need momentum in terms of kinetic energy, you can write p square is 2m into kinetic energy. So p will be root of 2m into kinetic energy. Relation between momentum kinetic energy, either p square by 2m is equal to kinetic energy, or momentum is equal to root of 2m into kinetic energy. Simple.